Okay, in this lesson, we're going to answer a couple questions that involve using the product and the quotient rules. We've seen these questions before. They have us write the equation of the tangent line at an indicated point. For our first example, we're given a quotient, so we're going to need the quotient rule. So I'm going to set myself up for that. F prime, G prime. Okay, F refers to the top function, which is x minus 1. G refers to the bottom function, which is x plus 1. The derivative of x minus 1 is 1, and the derivative of x plus 1 is also 1. With this information, I'm going to use the quotient rule to find the derivative. Well, according to the quotient rule, the derivative can be found by taking the bottom, multiplying it by the derivative of the top, minus the top, times the derivative of the bottom. And all of this is over the bottom function squared. So to reiterate, it's the bottom times the derivative of the top, minus the top times the derivative of the bottom. Some people who set their problems up like this say it's the product of the inner functions minus the product of the outer functions over the bottom squared. So if that helps you, feel free to use it. Cleaning this up, we end up getting on the numerator x plus 1 minus x plus 1 all over x plus 1 squared. The x and the negative x cancel out. So we're left with 2 over x plus 1 squared. So to write the equation of a line, we need the slope, and this is where the derivative comes in. Now the indicated point is when x is equal to 2, so we're going to plug that in for x. And we end up getting 2 over 2 plus 1 squared, which is 2/9. So that's the slope of the tangent line at that point. So using point slope form, we conclude the problem with y minus 1/3 is equal to 2/9 x minus 2. So again, nothing really too different from what we've done before, except now to find that derivative, we're going to need to use these two rules, in this case the quotient rule. Okay, for our second problem, it involves some trig, not a big deal. A previous lesson discussed the derivative of the trig function, so hopefully you have those memorized at this point. You're well on your way. The derivative of secant is secant x tan x. So again, to find the slope of the tangent line at a specific point, we're going to have to plug that into the derivative. So the specific x value is pi over 3. So this becomes the first derivative evaluated at pi over 3, secant pi over 3, tangent pi over 3. Okay, well the secant of pi over 3 is 2, and the tangent of pi over 3 is root 3. So our slope is 2 root 3. Using point slope form, we end up getting y minus 2 is equal to 2 root 3 times x minus pi over 3. So two examples of writing equations of tangent lines, a very common question in calculus. In this question, they ask us to determine the point or points at which the graph has a horizontal tangent line. We've seen this problem before, but just as a reminder, a horizontal tangent line would occur when the slope is equal to 0. And of course, the slope is like finding the first derivative. Before we do the calculus, I'm actually going to draw the graph of this so we can maybe anticipate where these points might occur before we do the calculus and see that it is confirmed. So I'm going to start by drawing a graph. When I look at this function, I realize that there are not going to be any vertical asymptotes, but there is going to be a horizontal asymptote at 1. going to have a y-intercept at 0, and also an x-intercept at 0 that's going to bounce. And one last observation that I'm making is that it's going to exhibit even symmetry, which is symmetry over the y-axis. So if I draw a picture of this, it's probably going to look something like that. Okay? So if we had to make a guess as to any points where there might be a horizontal tangent line, if I were to put a point here, it's going to have a negatively sloped tangent line. If I put a point here, it's going to have a positively sloped tangent line. But I'm thinking, if I were to put a point right here and draw the tangent line, it's probably going to look like this, which is a tangent line with a slope of 0. So I'm thinking, this is my guess, that 0, 0 is going to be my guess. And let's see if the calculus confirms that. So as we look at this problem, we have a quotient, so I'm going to use the quotient rule. So I'm going to set myself up and say f prime, g prime. It's a way of keeping my work organized. F is for the top function, x squared. G is for the bottom function, x squared plus 1. The derivative of x squared is 2x, and the derivative of x squared plus 1 is also 2x. So I'm ready to use the quotient rule, which says the derivative of a quotient is the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function. And all of this is over the bottom function squared. So just to reiterate, it's the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function. Some people who use this setup say the inners minus the outers, or the product of the inners minus the product of the outers. If that helps, then go for it. Cleaning this up a little bit, we end up getting 2x cubed plus 2x minus 2x cubed. And again, it's all over x squared plus 1 squared. The 2x cubed and the negative 2x cubed cancel out. So ultimately, we're left with 2x over x squared plus 1 squared. So this is the derivative, which is an expression for the slope of the tangent line at a certain point. And we want to know when that slope is going to be 0. So you're going to take that derivative, which is 2x over x squared plus 1 squared, and we're going to set it equal to 0, or in this case, 0 over 1. I cross multiply and I end up getting 2x is equal to 0, which means that x equals 0. When I plug in 0 into the original function, 0 squared over 0 squared plus 1, I end up getting a y value of 0. So consequently, the point at which there's going to be a horizontal tangent line is in fact 0, 0, just like we guessed it to be.